And so he came up with this word logarithm, and it comes from two Greek words, ratio, which means logos, and number, which is arithmos. So you sort of take this off and smash them together, and you can sort of see where it comes from. There's not really any other word in our language that's like logarithm, at least that I'm aware of. Anyhow, that's where it comes from. When you answer a logarithm, we've kind of been doing this. You basically ask yourself a question. So, like, you kind of think, basically, how many times do I need to multiply this number by itself to get this number? Right, yeah. Same thing as saying, like, 2 to what power is 8? So that's what the logarithm says. It's kind of good as a sentence. How many times do I multiply this one by to get that one? It turns out there's a lot of applications of logarithms. The one that we're going to look at today is the Richter scale. Does anybody know what the Richter scale is? Yeah, earthquakes. Everyone's on the Richter scale. So have you heard like a magnitude 4 earthquake or magnitude 8 earthquake? The scale of 1 to 10? Well, yeah, I'll show you the formula in just a second. Yeah. Does anybody know, anybody play guitar? Anybody here? I tried one time. I think so. So, the guitar, I'm bad at drawing, but so here's like an electric guitar, right? And then it's got this piece that goes out here. Alright, so there's your guitar. And the guitar has these lines that go kind of like this. Do you know what those are called? Strings. No. The strings, yeah, the frets, right. Strings go this way. So these are called frets. And the frets on the guitar are actually based off of a logarithm scale as well. They're smaller, and then the spaces get gradually wider as you go. It's actually based off of logarithms. The decibel, like the way you measure sounds for decibels, is based off logarithms. The pH scale, which have you guys done that in chemistry? Yeah. So like 7 is like neutral, right? If it's lower than that, it's acidic, and then about that space. That's based off of logarithms as well. So like an 8 versus a 9, like 9 is 10 times more than the 8. So on and so forth. Compound interest, population growth. These are both exponential, we talked about, but really anything that's exponential is also logarithmic because to solve an exponential equation, you got to use logarithms. So all of these things are based off of exponential / logarithms. And we're going to look a little bit more at this Richter scale for a couple minutes. This is the formula for the Richter scale here. The magnitude of an earthquake is the intensity divided by 10 to the negative 4th is how they come up with the magnitude. So they use like some instruments to figure out what the intensity is, and then they plug it into this formula. And here's what the Richter scale looks like. It increases as you go up, and each one increases by a factor of 10. So like 5 and under is really small, you probably wouldn't notice much, but then as you get, closer and closer to 10, 10 is the highest on the Richter scale. And this chart's kind of neat because it shows you the equivalent to like different energy releases, so like atomic bombs. So the Hiroshima bomb would be here, it would be like equivalent to like just over a 6 on the Richter scale. Because it comes with the amount of energy released. And if you remember that Star Bomba, you guys remember that with the nuclear? A little bit. So that was that giant nuclear missile that they tested. And it turns out there's earthquakes that are even more powerful than that. We've had 4 of them that we measured. One in Missouri in 1812, one in Japan, one in Alaska, one in Chile as well. So earthquakes can be super powerful, and they grow exponentially as you grow up. So like you can see, 2 would only be 123 pounds of energy released, same as that amount of explosive. Then it goes to like 4,000, and then 12,000, and then 4 million pounds, 123 million pounds. So you can see increasing 1 is going to increase the energy a lot more. And I got a little video. It's actually Bill Nye. He kind of explains that a little bit here. Here we go.
The Richter scale is a way to compare the size of one earthquake to the size of another. Now the ground can move in all different directions, but to start out with, let's say it's moving up and down, like this. See how we have a nice smooth curve? That's from the ground moving this way. Now let's say we have a bigger earthquake with a bigger ground motion. Let's say we have one 10 times as high. This. See how this one is 10 times higher than this one over here? So then the ground would take on a shape something like this. Same nice curved shape, but this stack of chips is 10 times as high as the one over there. But look how many more chips there are. You see, it takes a lot more chips to keep the curve in the same shape. The chips are like the energy in an earthquake. So when the ground moves 10 times as much, it has a lot more energy, about 32 times as much energy. And we have 32 times as many chips. Now, because the numbers can be very small or very large, Richter came up with the idea of using tens. So let's say we have an earthquake of magnitude 1. Well, it's going to have some ground motion. We'll call it 1. Now let's say we have another earthquake of magnitude 2. Well, its ground motion is going to be 10 times as much. We just add a 0. Then for an earthquake of magnitude 3, we add another 0. So look, an earthquake of magnitude 3 has 100 times the ground motion of an earthquake of magnitude 1. And it has a lot more energy. Now, since Richter came up with this, a lot of other scales have come along. But they all work in about the same way. The bigger the magnitude, the bigger the earthquake. And the bigger the energy there is to knock stuff over. You weren't supposed to see that.
Oh, sorry.
All right, so you get the idea. As you go up the Richter scale, it's like 10 times more powerful for each one. So it's kind of like it's also based off of tens, kind of like the metric system, where like there's 100 centimeters in a meter, and like there's 1,000 meters in a kilometer, based off of a 10 scale, which is better than our system. But one thing you'll notice is this log here doesn't have a number here, right? Yeah, it's a real picture. Yep. Yeah, I'm not sure where that one is. Wow. It looks fake. How the chunks of road, yeah. It's fake, but it is real. Anybody know what this number is? No number there. What is it?
1.
10. It's 10.
Yeah, it's 10. Yeah.
I remember that.
So this is a special logarithm. So when we don't write any number, it means a log base 10. And that's a special logarithm, which we're going to write down here. There's two important ones. That one with just the log is called the common logarithm. It's used a lot. And since it's really common, they just have a special symbol for it. Instead of writing log base 10, we just say log. And it actually means log base 10. And that's the one on your calculator. So it gets its own button. So know it's got to be important. There's only a few things that get their own button. Sine, cosine, tan, some of the exponents and stuff. And so it's pretty important to get their own button on the calculator. And so the way that we could solve this would be like, so if I said log 100, what would that be?
10.
Oh, it's 100 times 10.
1. It'd just be 100.
Okay, if I write a 10 here, what is it?
10,100.
10,000.
1,000.
It's 10 to the power of something to get 100.
2.
2, yeah, it's 2, yeah.
Oh.
10 to the second power is 100.
That's right. 10 times 10.
Alright.
You said something too.
What?
You said something else too.
No, I just said 2.
I know, but 10 before that. 10. It's 10.
I don't think I did.
No, what's log 1,000?
3.
3, yeah, 3. Yeah,
So
He
how many
said
zeros?
it in the video.
How many zeros there are?
yeah.
Oh.
So this is saying 10 to what power is this? 10 to what power is it?
That makes sense now.
Okay, now the other common one is called the natural logarithm. And this one I think you actually use even more in math than the common logarithm, just log. And that also has a button on the calculator. It's the one right below log, and it's an ln. I write it in cursive because it gets a little confusing if you write it like this, because sometimes you might think it's a 1. Like it could be like 1 and x. So I've always written it cursive like that, so it's less confusing. But it is, let's say ln on the calculator there.
L N or N?
ln. Like natural log. I don't know why it's ln instead of nl, but anyway. ln. And anybody know what this base is? If we were to write this as a base, log base, what?
10. 100.
Well, 10 was log.
X.
Nope. This one's actually log base e.
Oh.
That's just great. Now it's just loads. Right. Logics.
So we don't ever write log base e. We just write natural log x. But that's what that means.
What if it's LN?
Huh?
What if it's LN being long?
Long natural.
Long.
Log natural. Yeah, I don't know why they made it ln instead of nl. Probably because it makes more sense to write that way. I don't know.
It's O's first.
Long.
Oh, yeah, probably, yeah. So anyhow, you need to know that that means log base e. Okay. All right, let's get to the graphing here.
This is gonna be fun.
It's actually pretty easy. It's easy, like just as easy as exponential.
How many graphs?
We're gonna do 4, but this is gonna be the parent function first. All right, so this graph is gonna apply for any logarithm, so long as this number is bigger than 1. And that's all we're really gonna talk about right now. So this would be for log base 5, log base 10, log base e, so anything like that. And to get this graph, we can actually start with the exponential function. So I'm gonna draw the exponential, which so remember what that looks like. This is e to the x over 5 to the x, something like that, right? Well, if these are opposites, inverses, that means they're actually reflections of each other over this line y equals x. And this point is 0, 1. So if something is an inverse, all the x's and y's switch. So then when we do the natural log, it's going to have the point 1, 0. And everything just reverses. So it looks like, if you turn your head, you can see how it's just a reflection. So they're inverses of each other, meaning they're sort of just flipped. So this would be the natural log of x. It would also, it's going to be the same if you just do log x. If you did log 3. They're not all the same, but they all cross at the same spot. So I'll show you here what the difference would be on Desmos. So if we were to graph natural log of x, that's the same as log based e, right? Does anybody remember what e is as a number?
2.78.
2.817, yep. So that's the shape of that one. And then so what I have here is like increasingly bigger indexes here. So this is log 5. It crosses the same spot, but it just is a little less steep, if you will. Log x is the same as log 10, right? And it's even a little bit less steep. If I did like log 20, same thing. Log 100, same thing. So they all look the same. It's just going to be how steep it is. But when you're sketching it, you're not going to know the difference between a log 5 and a log 10 really. So don't worry too much about what it looks like. Just note that it goes down here, and it crosses, it goes like that, and it approaches here and never crosses 0. Right? Yeah. Crazy. You see that?
Oh,
It's
yes.
like slowly coming back.
When we draw it, it's
See?
back.
Yeah.
Oh, that's cool.
It's crazy. Anyways. All right, so the graph looks like this. It crosses here. And we're going to state all these things we always say, like domain, range, all that good stuff. And so again, this applies for like natural log, or just log, for really anything, log base 3, log base 5, whatever. They all look the same. What is the domain of this one?
1, 2, 3.
Close. Nope. How far does it go in the x?
Almost 0.
0 to infinity.
Yeah, 0 to infinity. It gets infinitely close to here without touching. There's actually an asymptote there. Everything is flipped from e to the x. So if you remember, e to the x, the domain was all reals, and the range was 0 to infinity. So this is going to get flipped. The domain and range is swapped. So this one has a range of all real numbers. Goes down, negative infinity, up to positive infinity. It's going to slowly get there. And e to the x did not have an x-intercept. This one does. It's at x equals 1. It had a y-intercept across there. This one doesn't. It never crosses. E to the x had a horizontal asymptote. This one doesn't. But it does have a vertical asymptote here at x equals 0. So that's going to be what we start with on all of our graphs. And then we're just going to do our transformations from there. As long as you know the transformations, though, it's the same stuff we've been doing. Anybody want a piece of graph paper?
Yes, yeah.
And then I was watching one of the people doing that Jeep, and he was like, my Jeep could make it like, you know, like Jeep.
Come on, bro.
My Jeep could make it of that. He just completely just rolls it.
My ADHD is not like a
How you want those fidget spinners?
I'll fidget with something. That's why I'm
I didn't
bouncing
take
my
it
leg
from
or
you.
something.
I don't
I didn't get it. Well, there's less in the.
Oh.
You didn't raise your hand, dummy.
Oh.
Sorry, I'm really tired, but I keep going.
Oh, thanks, Mr. Davis. You're so mean.
Yeah, like every time.
Thank you, Mr. Davis. Well, like I was mean to everybody. You're mean for no reason.
Facts. Facts.
For just no reason.
You
Especially
know what I've been
Jaden.
mean to
Especially
you?
Yesterday, anatomy.
When?
Like those mean to
And he was fucking
Oh, sorry, I
wrong.
didn't talk to you.
everybody. It's me.
All right, here we go.
I don't touch you.
So we're going to start with the parent function. So always just start by drawing it through one. We just got one transformation. What does that plus 4 do? Yep. It's inside, so that means left and right. This tells us to go left 4. Good. So we're going to take our dot, move it left 4 spaces. The other thing we have to move is the asymptote. It was at 0. So the asymptote is at negative 4. And that's that. So then we're going to write out our domain range and the vertical asymptote, all these. the domain, what's the new domain?
All.
Four.
Yeah. -4, because we shifted it over a 4, right? So now it goes all the way over to -4. The range always stays all real numbers. And then the vertical asymptote moves left 4 as well. So pretty easy. All you gotta do is get the shape down, and then it's all the same transformations as this. Okay, let's try one with the reflection. Still start with straight function there. So does this reflect over the x or the y?
X.
X, yeah. This is a reflect over the x. And then we also have to go outside, so it's going to be down. Hopefully by now you know all those because we've done it for a bunch of different functions. Then we should worry about
Boom. Roasted.
so then we get our reflected over the x. So this is going to go down, and this one goes up. With that. Reflected. And then we also got to go down 3. So here's our spot. Down 3. And go like that. Does domain, range, or asymptote, does any of that change from the parent function?
No.
None of them will change because domain, we didn't move it left or right, so domain's still going to be the same. Range still goes up forever, it still goes down, it just goes down slower. And then we didn't move the asymptote, so it's still good.
Hope said that you need to distinguish between a U and a V because she just asked me what a UA is.
Okay.
So
Alright. Fair enough.
it's okay. It was just her request.
Read verb what?
We should.
Sorry. That's a fair request.
Say that.
So you can do V sort of like that.
Yeah. Just for hope. Make it look like
Do
that
it.
for
Do it.
hope.
Make it look like a bird.
I guess that's Under Armour, right?
Yeah.
I don't even know what it would stand for.
That is universal artillery.
Oh.
Universal Artillery.
Okay.
In math?
Let's do this.
I was on
Alright, let's do one more. So this one's a log, but it works the same way as a natural log. And yeah, this one does have a stretch, right? Because it's multiplied. Stretch.
Right this. Right one. I don't want to say two.
And then we got a right one. Now let's see real quick what a stretch does. That's what's here. I'm gonna take these off real quick. So when we did e to the x, do you guys remember how the stretch like took it through a 2 instead?
Yeah.
Let me get rid of this. So if we had e to the x, and then if we put a 2 in front, it would make it go up through a 2. With logarithms, if I put natural log of x, if I put a 2, it doesn't actually change where it crosses because it's the different axis. It sort of just stretches it out. So you can see the difference here. Now what would happen if we put a 2 inside? That's what changes where it crosses. So when you put a 2 on the inside, it will change it. We'll do that tomorrow. But you can see on the outside, it won't change it. It just stretches it a little bit. On the inside is where it changes, where it crosses. So when we draw this, the stretch, we're just going to change it from this thing going through here, something like this maybe. Just show that you stretched it and just make it sort of grow faster like that. That might be too much, but just show that you're stretching a little bit. And then we also have to go right one. Move right one. That's the move one as well. It just pulls it out, stretches it a bit. And then domain, since we didn't move it to the right one, the domain shifts to the right one. Now it's 1 to infinity. Range is always all reals. And then the vertical asymptote is at x equals 1.
I was just really confused the first time.
Actually, it looks more like an R now.
You just keep overthinking it, then it just makes it all.
All right, you guys got to do 4 problems like this. So you can just do them on the back of that sheet there. 74, 75, 78, 79.
The horse tweaking.
Yeah, it's not racing. There we go. Alright. So there's your problems. It is on Google Classroom, and then the problems are up here as well. You just want to copy the problem what you can.